So let's start with 7.5, rationalizing denominators. And in my own view, this is probably the most important chapter or the most important topic in chapter 7.5. So what's going to happen is we know that we can have fractions a over b, where a and b are any real numbers, b is not equal to 0. So what happens if I have 1 over the square root of 2? And I really wish I knew the history behind this, and I don't. It's more pleasing to write this in an equivalent form. And writing this in an equivalent form is called rationalizing the denominator. Because just remember, numbers like the square root of 2, the square root of 5, the square root of any number x, where x is not equal to b squared for some b that is an integer, these are all irrational. There's an awful lot to be said about this. The square root of 2 literally has a decimal expansion that goes on forever and ever and ever without ever repeating. And I hope you have some bit of mathematical curiosity as to how we could know it goes on forever and ever and ever without repeating. At any rate, it's another subject for another time. We might do some small mini lectures in the 3rd floor of the library as soon as we're able to go back to campus. But let's just deal with 7.5. So we're going to rationalize a fraction. To rationalize a fraction with the radical in the denominator, any radical whatsoever, is to write the fraction in an equivalent form without a radical in the denominator. Some of you may have already done this, and if not, you're all going to be doing it right now. So our first example, which is 1a, is 2 on the square root of 5. So this is a real number. It's a 2, which is a real number, divided by another real number, so it's a real number. So whatever transformation I do with this fraction has to be the exact same value. So here is our key, one of our keys. If x is not equal to 0, then x divided by x is equal to 1, and 1 times b for any real number b is equal to b. That's the multiplicative identity of 1, and 1 has many disguises. And if you think about it, how many different choices of x exist where x is not equal to 0? Well, literally there's an infinite number of 1. So what we're going to do here is I have to multiply it by 1, and 1 is going to be disguised in the form of some number x divided by some other number x, where that number is never 0, and we'll never be tempted to use 0 anyway, so we can just kind of ignore that right now. So how do I choose x? I look at the radical that is on the denominator, and I use that as my value of x in the numerator and in the denominator. So our results is just basically multiplication of fractions. So this is 2 times the square root of 5. And this is the square root of 5 times the square root of 5, which is the square root of 5 squared. So the square root of 5 times the square root of 5 is another writing way of saying the square root of 5 squared, And from our last lecture, we reviewed that that's actually equal to 5. Just so you'll see, the square root of 5 squared is equal to the square root of 5 times the square root of 5, which is equal to the square root of 5 squared, which is 5 by definition. The whole point is, once we have removed the radical sign from the denominator, then we are done. So that's our final answer. I really do not know why mathematicians prefer it not to be in the denominator, but my guess is when they're wanting to add or subtract rational expressions, finding the LCD is an awful lot easier if we don't have radicals there. And that may be the only reason. So 2 times the square root of 16 over the square root of 9 times x. Now again, let's look at 16. It's 2 times 8 times 2 times 4 times 2 times 2. Well, how many 2's is that? That's 2 to the 4th. So that's the same as 2 squared. So let's just simplify that. 2 times the square root of 16 is the same thing as 2 times 2 squared. So I'm literally, before I do anything else, I'm going to simplify as much as I can. And down here, let's just recall that 9 is equal to 3 squared. So that's 3 squared times x. So let's simplify as much as we can. So here, remember, the index is 2. So the square root of 2 squared squared, so what dominates is this last exponent. So the square root of 2 squared squared is the base. This is the base. So this becomes 2 times 2 squared. Everything gets moved out from under the radical on the top. And down here, because remember our unwritten index is 2. So this 2 and this 2, if you want to think, cancel out. I don't like to do it that way. I just like to look at the base and say, okay, the base gets to escape from underneath the radical sign. And what remains behind is the x. So now let's go ahead and simplify what we have in the numerator. 2 times 2 squared is 2 times 4, which is 8 over 3 on the square root of x. And we're assuming x is not 0. So what I choose to multiply in the form of something divided by that same thing is I always choose the radical in its most simple form. There's absolutely nothing we could possibly do to simplify the square root of x. So I'm going to multiply it by the square root of x on the top and the bottom. That's 1. So multiplying 8 times the square root of x, I get 8 times the square root of x on the top. On the bottom, I get 3 times the square root of x squared. Why? Because 3 times the square root of x times the square root of x is 3 times the square root of x squared. I wrote 8 up there. That's supposed to be just a plain old x. So my final answer is going to be 8 times the square root of x over 3x. Okay. So rationalizing denominators is not so bad. We actually rationalize. If you can rationalize the numerator, if you can rationalize the denominator, you can also rationalize the numerator. I cannot think in my entire life when I've ever had to rationalize a denominator, but we will look at one example of that. So the first thing I'm going to do here is I'm going to use my quotient rule for radicals and write this as the cube root of 1 over the cube root of 2. And here, if you don't know what the cube root of 1 is, just realize 1 cubed is equal to 1. So I'm going to write this as the cube root of 1 cubed. And down here is going to be the cube root of 2. Well, the cube root of 1 cubed, well, the base gets to escape, and that's everything. So that's just 1. That just simplifies to 1. So this is equals. So this is the cube root of 2. So let's get some room over here. Erase this. Don't need it. It was rather obvious. Well, I hope it was obvious. So now what do? I have to take my fraction and I multiply it by some form of 1 disguised as x over x. And you always just take your most simplified radical expression. So that's the cube root of, let's stop for just a second. So I'm getting ready to just tell you the answer, but I think I need to explain something here. So I want to get rid of this radical. I want to change the cube root of 2. I want to multiply it by some radical so that I get the cube root of 2 cubed, which is the same as the cube root of 2 cubed. So what do I need to do? This right here gives me 1 power, but I need a total of 3 powers. So I have to multiply it by the cube root of 2 squared. So the cube root of 2 times the cube root of 2 squared is the cube root of 2 cubed, which is the cube root of 2 cubed, which is 2. So that is what I'm going to have to multiply. As my way out. I'm going to have to multiply both sides by the top and the bottom by the cube root of 2 squared. Let's get some more room here. Let's erase a few things. So notice, use parentheses of a different color. It's getting, I'm taking my original, after I simplified this as much as I could, I got this. And now comes the radicalization part. This has to be raised to the 3rd power, and it's only raised to the 1st. So I have to multiply it by 3, the cube root of 2 squared. And that's if I multiply it by 1 is what I'm multiplying it by. 1 written as the cube root of 2 squared over the cube root of 2 squared. So I'm going to get the cube root of 2 squared over 2. The whole point of that is we are rationalizing the denominator. And we just did. 2 is a rational number. But there's going to be more work to do in the simplification up here. That's the same as the cube root of 3 over 2 squared over 2. So that's the same thing as the cube root of 4 over 2. And that's it. It can no longer be further reduced. Remember what I said last time in the last lecture? A radical is fully reduced when all powers of the radicand, the expression under the radical, all powers raised to the index 3 have been removed. But 4 has nothing raised to the third power, only something raised to the second. So we are done when we get to that point. Okay, next one. Which is down below. So here, this is 2, just 2, not an A or a B. So this is 2. Just example 2. So this is going to be an invitation to use the quotient rule for radicals. So this is square root of 7 times x over the square root of 3y. Now this bottom radical cannot be in any way simplified. So the only thing to do now is to multiply it by some form of 1 in the form of some expression over the expression. And that expression always is the radical portion that cannot be further simplified, that is on the denominator. So the square root, so since the index is 2, then what I'm looking for is that radical squared. So when I square that radical, the square root of 3y squared is equal to 3y. So I'm going to get 3y on the bottom. And now I'm multiplying 2 radicals. So the nth root of a times the nth root of b, as long as these are real numbers, is equal to the nth root of a times b. So this is going to be the square root of 7x times 3y. So I can simplify that. 7 times 3 is 21, and x times y over 3y. And once we get it to that fashion, we are done in the sense that we have rationalized the denominator. The denominator is, I could find the LCD at 3y, right? Let's look at another example. Looks nastier than it is. That's always the case. You just have to go through and kind of have an idea of what's going on. This chapter, chapter 7 and chapter 6, is especially the reason we really want students who take intermediate algebra to have pretty solid skills As a matter of fact, everything except chapter 6 and chapter 7 and part of chapter 8 are are subjects that we deal with in our remedial class, math class, MATV 0028. And our observation over the years is that many students would be much better if they took that first. I don't know what goes on in high school. I have no idea. It's been years since I've been in high school. But you're not getting the math, or you're not, so many students are not held to the math standards needed when they get to school to feel comfortable. And many of you feel completely overwhelmed. And this is the fourth root of x. And here I literally have sympathy for you for being overwhelmed, because this is all new. Chapter 6 and chapter 7 is stuff you should have never, ever seen before. But many of you have been feeling overwhelmed from the very beginning. So again, the first thing we want to do is we want to simplify the denominator as much as we can. So 81 is equal to 9 squared, but 9 squared is 9 is 3 squared. So 81 is 3 squared squared, which is 3 to the 4th. That's not a coincidence. So 81, remember, I'm looking at my index for the powers that I want. So 81 is 3 to the 4th. And I can write y to the 5th is y to the 4th times y. And that's exactly how I'm going to write it. So I've got the fourth root of x in the top. And down here, I have the fourth root of 3 times y to the 4th power. That's just using the power of a product rule times y. Some more space here. Start simplifying down here. Again, I'm going to have the fourth root of x in the numerator. And now, since these indices are the same, the 3y gets to escape and come on the outside of the radical sign. But I have a y still there. So now let's identify my radical that cannot be further simplified. So it's the fourth root of y. Let me make this a little bit lighter. To the 1st power. So I want to raise it, multiply it by the fourth root of y by another power, such that 1 plus that other power gives me 4. So the answer here is 3. So what I'm going to do is I'm going to multiply top and bottom by 4. And this is going to be raised to the 3rd power. Let me write this. Let me give you another rule. I'm going to insist we use it. I think it'll be better if I go ahead and give you this. There we go. I'm going to rewrite that. We're still going to use this. Back a while ago, we learned, I think it's 2 lectures ago, we learned that the nth root, way too thick. That the nth root of x raised to the mth power is equal to the nth root of x raised to the m power. So let's apply that right up here. That's the same as, this part right here, is the same as to the fourth root of y to the fourth power. And that's what we're going to use when we rationalize. So I'm going to multiply this times the fourth root of y raised to the fourth power. The fourth root of y raised to the fourth power. So since the indices are the same, the top becomes the fourth root of x times y to the fourth. Down here I have 3y, and the very process of what I'm doing gives me the fourth root of y times, should have done this y to the third, sorry. I'm just now realizing that. Should be y to the third. And that's what I have written there, but I did not transfer it over here. This is the fourth lecture I've done today, taped. So my mind's just kind of wanting to stop. So that's the reason. That's the error right there, is screaming at me. One small place. And it carries over. Okay. So now we're good to go. So this is equal to, I'm going to go ahead and bring all of the simplification down to here. So there's nothing I can do to simplify the numerator. But this is 3y, and the fourth root of y times y cubed is the fourth root of y to the fourth, which is y. So the final answer is the fourth root of x y cubed over 3y squared. Not too bad, just one little problem with a copy error. So let's look at the next page. So this is a really important concept that we're going to be using, because eventually we're going to start talking about whoops, hit the wrong thing. We're going to be looking at complex numbers. And this concept that I'm getting ready to introduce you to now is called the conjugate. So let A and B be two numbers. Then A minus B is said to be the conjugate of A plus B. So it's really simple. If you have two things added, then you change the plus to a minus and you have the conjugate. For example, 5 minus the square root of 2 is the conjugate of 5 plus the square root of 2, and equally 5 plus the square root of 2 is the conjugate of 5 minus 2. I think I just said the exact same thing. But look what happens. Why do we care about this? The whole point is our beautiful old sum of squares formula. If I have A minus B times a plus b, then the result is a squared minus b squared. So the square root of 5 plus the square root of 2 times the square root of 5 minus the square root of 2 is the square root of 5 squared. That's supposed to be a minus. That's a typo right there. Sorry, people. I'm just now noticing that. So just recall that's supposed to be a minus. Minus the square root of 2 squared. So that's 5 minus 2, which is equal to 3. I will fix that, of course, now that I see it, and upload a new copy. So we're going to go ahead and we're going to use that fact to rationalize denominators that are sums. So let's do 4a. So whenever you have a denominator that is a sum, and one of the terms is a radical, and in these cases they're always going to be of index 2, then what we want to choose to do is look at this denominator, and if you want you can put it in parentheses, and I want to write over here its conjugate. So its conjugate's really easy. I just take the first term, 3 times the square root of 2, and I change the sign from plus to minus 4. And of course, if I do that on the bottom, I have to do that on the top as well because I'm really multiplying by 1. So the end result is going to be 2 times 3 on the square root of 2 minus 4 over, let's come down here, this is 3 on the square root of 2 plus 4 times 3 on the square root of 2 minus 4. So that's like a plus b times a minus b. And we know this is equal to a squared minus b squared. So since a is 3 on the square root of 2, this is equal to 3 on the square root of 2 squared minus, and our b is 4 squared. So 3 on the square root of 2 squared is 3 squared times the square root of 2 squared minus 16. 3 squared is 9. The square root of 2 squared is 2. So it's 9 times 2 minus 16. So that's 18 minus 16. So that's equal to 2. So that's the value of my denominator here. Now how nice that I did all of this work down here before I did anything up here. Because now the numerator and the denominator both have a factor of 2. And that's going to cancel out. And our end result is just 3 times the square root of 2 minus 4. So this trick of when you have a sum, and the trick of using this formula right here, requires that we're going to be dealing with radicals of index 2. So you're going to be looking for square roots. So let's do number 4b. So I have the square root of 6 plus 2 over the square root of 5 minus the square root of 3. So what I want to do is I want to multiply by the conjugate. I'm not going to add this. I think it's annoying. I'm not going to add this extra parentheses. I'm just going to use a dot for multiplication. I'm just going to use that dot. So I'm going to use the, because I want to put this in parentheses. And I want you to put that in parentheses as well. So I want you to write the conjugate of this. Well, the conjugate is the first. All I do is I change the sign. And whatever is in the denominator must also be in the numerator because I'm multiplying by 1. So the numerator is the square root of 6 plus 2 times the square root of 5 plus 3. And down here I'm going to use the difference of squares. So this is the square root of 5 squared. In other words, a squared minus b squared. Minus, and my b is the square root of 3 squared. So you can do it in two ways. We have to figure out what the top is. We've done this in another lecture, so I'm just going to do it. This is the square root of 6 times the square root of 5. So that's the square root of 6 times 5, which is the square root of 30. Square root of 6 times 3. So that's plus 3 on the square root of 6. 2 times the square root of 5. And 2 times 3 is 6. And down here, the square root of 5 squared is 5. The square root of 3 squared is 3. So the whole thing becomes 5 minus 3 is 2. And the top cannot be simplified because 6 and 5 share no common factors. So when I multiply the square root of 6 times the square root of 5, I get the square root of 6 times 5, which is the square root of 30. There's nothing I can do to simplify it. In other words, there is no, what am I looking for? 30 is equal to 3 times 10, which is 2 times 5. So it's 2 times 3 times 5. There are no squares or even exponents there. So done. I can't simplify it. This is literally considered a simplification. And it is a simplification if you have to add them or subtract them, because I can find the LCD of 2, whereas finding the LCD of the square root of 5 minus the square root of 3 would be next to impossible. I don't know how to do it other than the way we would just do it. So this is 4c. So this is 2 on the square root of m over 3 on the square root of x plus the square root of m. So I'm going to put that in parentheses. And then I'm going to write down here the conjugate of this. So this is going to be 3 times the square root of x. Since that's a plus, it's going to become a minus, times the square root of m. And this is going to be the exact same thing. And of course, we're assuming the square root of 3 times x minus the square root of m is non-zero. So this top is going to be 2 on the square root of m, the numerator, times 3 on the square root of x minus the square root of m. That we'll be able to simplify this. Down here, it's going to be 3 on the square root of x squared minus the square root of m squared. So we're going to go ahead and simplify this all at once. 2 times the square root of n times 3 times the square root of x is 2 times 3, which is 6. Square root of m times the square root of x is the square root of xm. Or if you want to put mx, it does not matter. 2 times the square root of m times minus the square root of m is 2 times minus 1, which is minus 2, times the square root of m times the square root of m, which is the square root of m squared, which is m. Be careful here. This is one of the most common problems. You have to use the fact that a times b squared is equal to a squared times b squared. So 3 times the square root of x squared is 3 squared times the square root of x squared, which is 9x. Using the same there, we don't need it because the square root of m squared is m. And that's as far as you can simplify it. And you quit right there. And we have one more problem. And I'm going to show you how to do it. It won't be on any test that I write for you. But I can imagine it does occur in some instances where you might want to do this. So in this case, we want to rationalize the numerator. Suppose you wanted the numerator as rational rather than the denominator. So you're just going to do the exact same thing. Square root of 7 cannot be simplified. The square root of 45 is 9 times 5. So before we do anything, let's simplify. As we said, the numerator, 7 is prime. It can't be simplified. But 9 is 3 squared times 5. So that allows us to simplify it into the following. So the 3 squared can come out. It sheds its exponent. So these two are equivalent. So this and this are equal. But now I want to rationalize the denominator. So I don't want to put it equals there. I want to transform it by multiplying it by 1 in disguise. So what I have to do is now choose the numerator first. And that's going to be the square root of 7 times the square root of 7. Let's give me some room over here. So that's equal to the square root of 7 times the square root of 7 is 7. 3 times the square root of 5 times the square root of 7. It's all equal to 7 stays up there. 3 times the square root of 5 times 7, which is 35. So it's 7/3. 7 divided by 3 times the square root of 35. And now notice that the end result was our denominator became a rational number. And that's the last example from 7.5. I do feel that the techniques in this particular section are most important. And the most important examples, I think, will be the examples that we find on example 4 when we use the conjugate. Don't worry about rationalizing the numerator, but look at example 1a, 1b, and 1c. Look at all those, and you should be okay.